In today's notes, I'm going to teach you about another method for solving a system of equations. This method is called reduced row echelon form, or another name that you may commonly hear for this method is called, AKA by the way, stands for also known as. This is also known as what's called the Gauss-Jordan process. So you're already familiar with Gauss. Gauss is the one who came up with Gaussian elimination, Friedrich Gauss. There was a second mathematician who came along later, and his name was Jordan, and he wasn't entirely happy with the Gaussian process. Particularly, Jordan wasn't happy with the fact that you had to put the letters back in to the equations at the end to find the solutions. So he invented a technique which piggybacks onto the Gaussian elimination process to actually eliminate everything in the coefficient matrix except for the diagonal of ones. So let me give you the explanation of how this works. Reduced row echelon form is when you start by completing the Gaussian elimination process to get yourself into row echelon form. Up to here, this is exactly what you've already learned how to do, the Gaussian elimination process. We start from the top row, we work our way down, we work from left to right, we're turning the leading coefficient into ones, and we're getting a triangle of zeros underneath that diagonal of ones. So once you finish with the row echelon form part, this is when the Jordan part of this process begins. So the first part is Gauss, and the second part is Jordan. The Jordan part of the process uses rows that are underneath your diagonal of ones to eliminate any coefficients above the diagonal of ones. In this Jordan part of the process, you're going to work from the bottom up, and you're going to be working from right to left. So those two things are completely backwards from the way that Gauss processes things. But you can't do this Jordan part until you're already in row echelon form. So let's take a quick look at a matrix that is already in row echelon form. So here's our example. You've got your diagonal of ones and a triangle of zeros underneath it. So this augmented matrix right here is already in row echelon form. The Gauss process would have you put the ladders back into the bottom row to figure out that the answer for z was -2. Then you could put the letters back into the row above it, as well as the answer for z, and you could figure out the answer for y is 0. And then you could put the letters back into the top row, plugging in the values for y and plugging in the values for z, just like we've done in the past, and you figure out the answer for x is 8. So this, if we did things this way, this would be the normal Gaussian elimination process, getting yourself into row echelon form and then back substituting. But this part right here with putting the letters back in to figure out the answers for z and y and x eventually, that was the part that Jordan wasn't happy with. So what Jordan does is Jordan uses the bottom row, in particular this spot right here, to help him eliminate the -1 that's above the diagonal. So we're working from the bottom up. And so what would happen next is I would take the bottom row and add it with the middle row. Remember, I'm only trying to make a change to my middle row. So adding the bottom row to the middle row gives you a 0. Adding the bottom row to the middle row gives you a 1. Adding the bottom row to the middle row actually produces a 0 right here. And adding -2 and +2 makes 0 right here. So now your new middle row would be 0, 1, 0, 0. And if you put the letters back into that, that tells you the answer for y is 0. Exactly what we found up here by doing back substitution. Now, the Jordan part of the process is not done until everything above the diagonal of ones has been turned into zeros. The next thing is you use the bottom row multiplied by a -2 so that you could add with the top row to get rid of this 2 right here. So let's do that math. -2 times 0, add with this, still is a 1. -2 times this is 0, add with that is still a -1. -2 times this, add with this, turns that into a 0. And -2 times this is 4, added with 4 makes 8. So your new top row at this point would be 1, -1, 0, 8. Rows 2 and 3 remain the same because we didn't make any changes to those. Now, we're almost finished with the Jordan part of this process, except there's still one spot above the diagonal of ones that's not a 0 right here. And so you would use the middle row, since that's in the second column, you'd use the middle row to help you get rid of that -1. And we would simply just add row 2 and row 1 together. 0 plus 1 makes 1, 1 plus -1 makes 0, 0 plus 0 makes 0, 0 plus 8 makes 8. So the top row would be 1, 0, 0, 8. And if you were to put the letters back into the top row at this point, it would tell you the answer for x is 8. So one of the benefits to the reduced row echelon form is you'll get a diagonal of 1s, a triangle of 0s underneath the diagonal of 1s, and a triangle of 0s above the diagonal of 1s. So literally, when you put the letters back into this, it is just telling you the answer for z is -2, the answer for y is 0, and the answer for x is 8. So this saves that whole back substitution thing that you normally have to do from the Gaussian elimination process. Now, a lot of people at first don't like this process because there's all this extra work, and most people would decide they just want to do the back substitution and get their answers. But this process is going to be necessary for something that we learn later in the week called inverses. So you will have to know how to do this. And I will tell you one other thing. Eventually, I will show you how to do all of this work on a calculator. And if somebody else was doing the work for you, you wouldn't want to stop here because you'd still have to do the back substitution. If somebody else, namely your calculator, was going to do the work for you, you'd want it to go all the way to this form where you could literally just read the answers right out of the matrix. The second thing that I want to show you in today's notes is an application for all this knowledge of how to solve systems of equations. So the thing that I'm going to teach you today that has to do with using Gaussian elimination in a matrix form is something called curve fitting. And this is when we try to find the equation of a curve by knowing points that it passes through. So we all know that the general equation of a parabola is given by y equals ax squared plus bx plus c. This is the general equation for a parabola. But what if you didn't know the formula for the parabola, but you did know 3 points that it passed through? And I'll come back to why exactly does it have to be 3 points? Why not 2? Why not 4? Why not 17 points? How come it's got to be 3 points? We'll come back to that in a minute. What if you knew 3 points that the parabola passed through? Well, what you could do is you could substitute the x and y coordinates from each point into the general equation. Now remember, the x coordinate would go here, and the x coordinate would also go here, and the y coordinate would go right there. So the x's and the y's in this particular equation would no longer be the variables. They would be the things that you know. And what that means then in this equation is that the variables would be the 3 coefficients, a, b, and c. And if there are 3 things that we do not know, namely a, b, and c, then we're going to need 3 equations to help us solve that problem. And if we need 3 equations, that means we're going to need 3 points to give us the x and y coordinates so that we can create those equations. Once you've gone through this process of creating the equations by plugging the x's and y's in, and then go through the process of using Gaussian elimination to solve for the variables a, b, and c, so once you end up knowing the values of a, b, and c, you're going to have to plug them back into the formula where they belong. So a is the number that comes in front of x squared, b is the number that goes in front of regular x, and c would be the constant at the end. Make sure that you make it an equation by setting it equal to y or setting it equal to f of x. So here is our first example of curve fitting. And in this particular problem, I'm asking you to find the equation of a parabola that passes through these 3 points. The first point is -1, 3. The second point is going to be 1, 1. And the third point is going to be 2, 6. Now, the one thing that I would encourage you to do here is make sure you write down the formula for the general equation of a parabola. In this case, y equals ax squared plus bx plus c. That's going to be the formula that we keep referring back to. So this is going to eventually use the Gaussian elimination process, but what happens in this problem is first, you must create the equations. So what I'm going to do here first is I'm going to take the first point, and I'm going to plug -1 into my formula everywhere the x's go. So -1 is going to go in here as the x value and get squared. That's going to make a +1. The -1 is going to go in here and get multiplied with b, which is going to make -1 times b. And this is going to make +1 times a. And the value of 3, which is your y coordinate, it's going to go right here. So the first equation that I'm going to generate is going to be 1a minus 1b plus c equals 3. That's the result of plugging in the x and y coordinates into the general equation of the parabola. That helps me generate my first equation. The second equation is going to be created by putting in the second pair of coordinates. 1 is going to be my x value and is going to go in here and here. And 1 is also my y coordinate, which is going to go in here. And that would generate the equation 1a plus 1b plus 1c equals 1. Finally, your third pair of coordinates, 2, 6, are going to be put into the general equation for the parabola. 2 is your x coordinate, so it's going to go in here and get squared, which is 4, and then multiplied with a. 2 is also your x coordinate going in here, multiplying with b, so that's going to be 2b plus c. And 6 is your y coordinate going right here. So that equation would look like this. 4a plus 2b plus c equals 6. So here is our 3 equations. So our first variable is a, all lined up in a nice neat column. Our second variable is b, all lined up in a nice neat column. And our third variable is c. And we've got our constants on the right-hand side of the equal sign. So I just flipped where the y's were from the left-hand side over to the right-hand side. The next thing you do to help you solve this problem is you would create an augmented matrix out of this system of equations. So I would take these equations, remove the a's, b's, and c's, and turn into this augmented matrix. 1, -1, 1, 3 comes from the top equation. 1, 1, 1, 1 comes from my second equation. And 4, 2, 1, 6 comes from the equation across the bottom. Now I'm going to perform the Gaussian elimination process to help me solve this system of equations in an augmented matrix form. We always start with the top left corner, and we always want that top left corner to be a 1. Good news, it already is a 1. Now I'm going to use the top row to help me eliminate this 1 right here. And in fact, I would have to actually negate the top row and add it with the middle row to turn that into a 0. So that would turn into 0, 2, 0, -2 for my middle row. The top row is untouched, and I haven't even started working on the bottom row yet, so there's nothing that I did down here. So the next thing you'd want to do is turn this spot where there's a 2. You would want to turn that spot into a 1. So you'd have to divide everything in the middle row by 2. And that's going to look like this. 0, 1, 0, -1. So my top row is good, my middle row is good, and the next thing you'd want to do is start working on your third row, which has a 4 in the first position. We'd like to turn that 4 into a 0. You always use the top row to help you eliminate things in the first column. And if you add these two things together, that would make 5. So we have to multiply the top row by -4 before adding it with the bottom row. -4 times 1 is -4, added with this, that into a 0. -4 times this, added with that makes that a 6. -4 times this, added with that makes -3. And -4 times this, added with this makes -6. So your new bottom row would be 0, 6, -3, -6. The bottom row is looking better, but that spot right there where the 6 is, we want to turn that into a 0 as well. We always use the second row to help us get rid of things in the second column, and adding these together would make 7 right now, so you'd have to multiply the middle row by -6 before adding it with the bottom. This will give you a new bottom row of 0, 0, -3, 0, 0, -3, 0. And the last thing you'd want to do to put this completely in row echelon form is divide the entire bottom row by -3, making your new bottom row 0, 0, 1, 0. You are now in row echelon form. So we've got this diagonal of 1s, and we've got our triangle of 0s underneath it. It would be time to put the letters back into this problem and solve for your answers for A, B, and C. So The bottom row actually tells me the answers for C is 0. The middle row is actually telling you the answer for B is -1. And then by putting the letters back into the top row, you would have A plus -1 times the value of B, which was -1, plus 1 times the value of C, which was 0, is equal to 3. So multiplying this together is 2, and that's nothing. So A plus 2 makes 3, and that means A is 1. I'm sorry. A plus 1 plus 0 makes 3, so A is 2. So now that you've found the values of A, B, and C, the last thing to do is actually put these values back into the formula and make an equation out of it. So remember, A is the number that comes in front of x squared, B is the number that comes in front of regular x, and C would be the constant on the end, but it was 0. So your final equation for this parabola would be y equals 2x squared minus x. The last thing that I want to show you in these notes, which is something that you're actually going to use in the homework assignment that goes with these notes, is that you could take this concept and you could expand it out to any polynomial as long as you have as many equations as you have variables. So remember, to solve a system of equations, the number of variables and the number of equations must be a perfect match. If you have 3 unknowns, you have to have 3 equations. If you have more unknowns, then you better have that many equations. So for example, and this is the one that you're going to have to do for the homework assignment, a cubic, which is defined by this formula, y equals ax cubed plus bx squared plus cx plus d, how many points would you need in order to be able to curve fit a cubic? Now remember, if they're going to be giving us the points, that means they're giving us the x and the y coordinates. So the x's would go in here, here, and here, and the y coordinate would go in right here. That means the x's and y's are not the variables for this problem if they're going to give you the coordinates. What are the variables for this problem are the a, b, c, and d coefficients. So how many points would you need to be able to curve fit a cubic? The answer to that is you would need 4 points to help you generate 4 equations because there's 4 variables. So if I gave you 4 different sets of x and y coordinates, you could plug them in here to generate 4 different equations that you would then be able to use to solve for the answers of A, B, C, and D. Again, remember, once you find the answers for A, B, C, and D, you would want to plug them back into the formula for a cubic so that you actually have the full equation. Don't forget to set it equal to y or f of x. Okay, you are now ready to try homework number 130, which is going to have you do some curve fit.